Okay, so for those of you who I didn't introduce myself to, I'm Jeff Denworth. I'm the Vice President of Marketing for DDN. I've been at DDN for now 5 years almost, formerly at a little company called Cluster File Systems that a few of you may be familiar with. Eric Barton is a colleague of mine from there. Okay, so I've been asked to update everybody on the product set as it exists today and going forward to tomorrow. Talking about roadmap stuff in a public forum is a little bit of a dicey proposition. So what I wanted to do, thanks Larry. What I wanted to do was do a few things. One was to give everybody basically just a quick product overview of everything that we sell. People tend to consider us as an array provider, but the reality is that an increasingly smaller amount of our business comes from just base array sales, and what we are selling more and more of is solutions that include turnkey file systems that we're deploying, as well as some interesting products that we have going forward. Yost had alluded to our object storage system called WASP. This is an example of some of the things that we're bringing forward. Then I want to talk a little bit about why we do certain things. The design tenets that our engineering organization lives by, and some of the challenges that we're tackling every day as we build and deploy products. Then I'm going to give you a product update, what we have coming out actually this month, and then some roadmap highlights of what we see going forward. So the product portfolio today is a collection of very high-speed, extremely scalable array products that we couple very often with file-based solutions, whether it's a Lustre-based product like our Scalar system, whether it's a gpfs-based product like our Grid Scalar system, or other value-added file services. What we do is we basically have an entire engineering team within the organization that's designed around building up integrated delivery tools, oftentimes management tools, as well as optimizing the systems and building up best practices around how to deploy and how to manage these technologies. And there's a level of flexibility that we apply to the design of these technologies so that they support a number of the different arrays in our portfolio, ranging from the S2A6620, which is a low-end kind of modular storage system that we've designed principally for our channel partners, going from the 9900, which was already presented on by both Yost and Sanzio, and the 10000, which is currently the world's fastest mid-range system from both a bandwidth and an IOPS perspective. And then finally, we'll touch slightly on our WASP product and some of the integrations that we've done with organizations like iRods, as well as our perspective of that for what we call hyperscale. So, so not getting into Pro, actually I can move this. Excuse me. There we go. So just a quick introduction to a product that we've announced at NAB, which is a media trade show in March, that we haven't yet had an opportunity to, I guess, introduce to the high-performance computing community. A system called Scalar that we're starting to ship at the end of this month. It's the world's, we believe, the world's first fully featured enterprise file storage system that's designed for a very high degree of flexibility and eliminates over-provisioning for deploying for big data applications and large content applications. So Scalar is in effect a scale-up, scale-out NAS platform that is modularly configured. When we say fully featured, we mean that the system comes with all sorts of data protection, data management tools that, sorry, this is very strange, that comes with all sorts of data management and data protection tools that we don't charge additional for. So it's a no surprises, high frills product that we brought to market that features all sorts of data protection capabilities like mirroring and asynchronous replication, things like snapshots and file cloning. And then moving forward into backup, we support things like direct native fiber channel based backup, which is much faster than NDMP, as well as an NDMP offering for people that are more comfortable with that. Because it is an enterprise NAS platform, it has support for all sorts of enterprise NAS protocols, anything from NFS, CIFS, FTP, HTTP, but also has enterprise management and data management features, things like a rich graphical user interface we built for it, very non-disruptive scaling. Our customers don't know how their data is going to grow and they want to prepare themselves for the unpredictable. A non-disruptively scalable system is key for that, particularly because it is an enterprise product. And then finally, it's a multi-tiered system. There's an automated facility within the system that leverages our ability to combine SATA, SAS, and SSD technology into a single array. And the NAS Scalar product will federate all of that data into a single file system and automatically manage data on and off of varying types of tiers based upon that data. So that's really the only real product overview that I'm going to give for this part of the presentation. What I wanted to do, aside from getting my laptop to work, is talk to you about why we do certain things. So in our engineering group, we have this concept of what we call defense in depth. And where this comes from is basically after having deployed more bandwidth to the top 500 systems in the world than all other companies combined. We have an awareness and a high degree of sensitivity to the complexity of deploying extremely large systems and the challenges that come along with that associated with things like drive rebuilds across a collection of hard drives that range into the thousands to tens of thousands. The amount of performance that needs to be maintained in a scale-out file system and the variances that scale-out file systems are sensitive to. Mean time to data loss is becoming an increasingly critical issue as people start to look at very large capacity hard drives, which are still very popular within high performance computing, things like 3 terabyte, and even looking forward to 4 terabyte hard drives. Rebuilds for these types of technologies can take upwards of days now. And all of this must live, we believe, in an environment that is not subject to compromise. So Sanzio had talked a little bit about sustained performance as opposed to benchmark or data sheet or kind of lab performance. And this is absolutely what drives DDN. It's achieving that level of sustained performance with less resources, with less equipment, and with a lower total cost of ownership than our competitors. So we continue to provide value to all of you. And then finally, looking at Amdahl's law, what that really means when you start to consider some scale-out conventions. So first, we'll talk a little bit about hard drives. Hard drives today are continuing to get large. We're looking at 3 terabyte hard drives now shipping in 2011 this quarter. Those have across all the hard drives, the SATA hard drives built today, they have a common error rate, which is around 1 to 10 to the 15th bits read, which means that as these drives get larger, there's just more bits that are getting read, and as a result, the data corruption possibilities continue to mount as drives increase in size. RAID 5, we believe, is basically met its notional, life expectancy, and you can find across IT publications all over the place, in addition to a lot of IEEE publications, the concept that RAID 5 for SATA is basically a non-starter these days. So as a result, people are looking at things like RAID 6 and evolved data protection mechanisms such as triple parity, which is costly because you're deploying, on average, an additional 8% more storage resources. And all of this rolls into just increased complexity that our customers are dealing with. And our drive, our thrust, our focus is minimizing this complexity to the greatest degree possible. So as one of the leading suppliers to what I call the very upper echelon of the top 500, we're involved in very large projects that tend to be forward-looking. Some of those projects are roughly approaching around 10 petaflops in peak performance, and the file systems for these systems that support them today are looking at about 1 terabyte per second of what I'll call peak bandwidth, and 50 petabytes of usable capacity has been floated around as a reasonable average. If I look into 2012, that system gets built with 15,000 4 terabyte hard drives and about 1,500 LUNs that assemble into a scale-out file system. Based upon what we've observed from our entire installation base, our drive AFR for SATA hard drives is around 3% annually. What does this mean for a 10 petaflop system? It means that our customers are going to be dealing with about 1.2 drive failures per day. DDN doesn't make hard drives. We buy best-of-breed hard drives from our suppliers that our competition also buys from as well. And at the end of the day, we don't make hard drives any differently, or we don't deploy hard drives any differently than our customers. So this 1.2 drive failures per day is basically a constant that's external to DDN. This is just something that the industry will have to wrestle with. When we talk about defense in depth, we need to talk about performance protection. And a drive rebuild for conventional systems has severe performance impact that we've actually measured. And defense in depth means that we need to continue to be mindful of the sustained performance as we deploy systems, because at 1.2 drive failures per day, you're always rebuilding. You're always in a state of degradation, and minimizing that degradation will dictate how file systems perform on average, not just in a degraded mode. So in preparing for these 10 petaflop or so type deployments, we started to do some real analysis within our engineering team. In partnership with one of our customers, we did a comparison of an SFA deployment versus a system that was built with software RAID. This is Linux software RAID. It is fairly intelligent in that it has the ability to do data-only rebuilds. So this is an advanced next-generation Linux file system. But whereas we initially thought that that would be a real boon to the Linux software RAID's capabilities, what we found is that these technologies aren't really built for this notion of defense in depth. And when you look at what we optimize our systems for, we're optimizing for basically two capabilities. One is we want to be able to rebuild systems and rebuild drives as fast as we possibly can. Secondarily, we need to minimize the performance impact of that rebuild event so that the sustained performance of the system, which is always rebuilding because of these very large drives and high capacity drives, we need to be able to protect the performance when it's in an average state, and that average is basically in a rebuild mode. And what we found is that even with the smartest software RAID out there today, the rebuilds are actually in effect very slow on commodity but high performance systems, and the performance cannot be maintained because these systems weren't designed to protect performance during rebuild state. So our customer had considered a best case where 50% of his performance would be reduced when he was doing a rebuild. But the worst case, what we actually saw in production, was a 63% performance degradation. Now, if you consider that the system is always in a rebuild state, that means that their best case 1 terabyte file system, which is, 1 terabyte a second file system, I think these calculations are actually around 900 gigabytes a second. You're seeing, at best case, 455 gigabytes a second, at worst case, 233. So when you're building a 50 petabyte system, it costs upwards of $10 million plus. That's roughly a $5 million delta in aggregate performance difference if you take aside, or you take out the capacity storage requirement. That's a $5 million difference or so in the capabilities of the system that the customer's throwing on the floor by making that software RAID difference. And so how do we get to that? Well, so we have a system architecture that's designed for extremely large backend bandwidth. That buys us a few things. First, it buys us the ability to perform all sorts of data services on the back end, ranging from parity protection to rebuilds to restarts to any sort of other drive anomaly correction event without having to forsake any front-end performance. So our backend is notionally a storage area network. But how we've architected the backend is a zero daisy chain model, or notionally a zero daisy chain model within 10 enclosures. And we stripe our data across all 10 of these enclosures that allows us to avoid things like daisy chaining for each I/O, and also we have the ability to withstand up to 20% of the resources in the system getting taken offline while still providing data services without any impact. So not only is it a resilient architecture, it's designed for performance in depth and defense of that performance in depth. So what does this look like in a real environment? we're increasingly seeing that customers are starting to very much be mindful of their performance as they look at an aggregated and an expected lifespan of the system and how different types of software interoperates with, different types of storage software interoperates with a common pool of drives. And what we found is that the peak average performance of our system is substantially higher than a Linux file system based capability because of this defense in depth. And it's not just Linux file systems, it's really across every single conventional storage architecture out there. Performance protection tends to be a secondary thought. But what this adds up to is really no more than a 10% peak performance drop for rebuilds with our architecture versus upwards of 66% if you assume the worst case with the competition. However, so defense in depth also relates to data integrity, and I think Jos was talking a little bit about what we're doing today to make sure that archives are managed with the maximum degree of data integrity. Defense in depth for us means implementing these types of solutions without having to forsake performance. So we do offer today things like checksums and parity calculation on every read, which ensures that as corrupted data is coming off of SATA drives, which is a common event, none of this is exposed to the applications. Secondarily, we have the ability as well with our system, as we did with the S2As, to do parity calculation for every read as well, if you're especially paranoid. But we were finding that the number of anomalies, I think at Oak Ridge we saw something in the range of over 10,000 hard drives, something in the order of about 200 bit error rates caught and corrected in a year's time. So the requirement to have real-time correction for that type of data is not really, it's of course you need to catch it, but you may not need to correct it in real time. And then in addition to that, for archive environments, we have things like background parity scrubbing that make sure that all of the data is consistent while it's at rest. And then, of course, we have all sorts of cache protection because we're increasingly being introduced in multi-threaded environments. We're looking at instances where caching is becoming increasingly important because the randomness that's coming from all of the I/O threading in very large scalable HPC systems tends to reduce the amount of sequentiality that a system can maintain. The nice thing about all this technology is it's a baseline for a real-time capability that we'll be building into the SFA platform that a lot of our customers were familiar with the S2A. So defense in depth basically means being able to deliver this type of data protection without having to lose any performance. So that doesn't work. What I was going to try to do is just move the screen just a little bit to the left. But what you see here is a comparison of our system with just parity checking on reads, parity checking with diff, and with SATA sure off. Now this is a write example, so parity checking on reads probably isn't so relevant, but in terms of the amount of bandwidth that you forsake when you're doing these types of additional data protection mechanisms, you'll see that there is no difference for DDN when we're going the extra mile to make sure that data is consistent and very high performance. The nice thing about this graph here, this is just one of the sample outputs that we've gotten from our engineering group. We're going to be talking a little bit about our new 6 gigabit very high density drive enclosure. For those of you that are considering SFA 10,000s, going forward, this new drive enclosure will increase the peak capability of the system by about 10% in terms of the bandwidth it can withstand. So one of the other key design tenets that we've started to introduce as early as 2009 was this notion of InStore Computing. And in a basic manner, this ability to host services within the array allows us to, at a minimum, eliminate file system networking, file system gateway services from an architecture, and just embed all of these processes within our platform. The more interesting aspect for our research user group is that it also supports hosted applications that run on x86 processing. So we now have the ability to basically build a system that's scalable in 3 dimensions: throughput, computation, and capacity. And this ability to support computation is not so much that we're going in and saying, okay, we're now the world's leading cluster vendor as well. But what we are saying is there are opportunities for very data-intensive and latency-sensitive processes to be hosted natively within the array. And what that allows for is basically data pre- and post-processing that doesn't happen on the network, doesn't congest the network, and you're starting to see some use cases of this in the marketplace today. We're working with a seismic processing company, for example, who's doing all of their I/O services within the SFA 10,000, and as a result, their network is considerably less congested. But of course, at a minimum, this capability lends itself to the construction and the engineering of appliances. We're starting with our Grid Scalar and our Exascalar platforms. These are our Lustre and gpfs-based products. It's highly amenable to parallel file systems, where you just take these appliances, put them onto the network, and you scale up your resources based upon your requirements. Of course, with DDN architecture, you have the ability to scale deep for capacity, or you can scale wide for performance, and the choice is yours. But what you don't have is storage gateways. What you don't have is storage networking. But the other nice thing about this is it also reduces file system licenses. I know Eric probably doesn't like that so much, but the ability to combine as many as 4 to 8 file system gateways into a single active-active storage system allows you to reduce your licensing costs as well. So the system architecture is actually built with a highly modified version of KVM that we built into the system, where basically you get bare metal as a resource that you can deploy your own way, if you work in tandem with DDN's field engineering team. Or what you'll get is a pre-configured and pre-optimized set of either OSSs or NSDs that live within the system that plug just directly into your network and are easy to deploy. So this is a fairly straightforward depiction of how gpfs, for example, embedded on the SFA, just reduces the amount of infrastructure required substantially to get to a common metric. So we'll extend this computation capability to many more interesting things that I'll talk about later in the talk when we talk about our roadmap. But I just want to get to the last very key design tenet that we build our systems by today, which is efficiency. And efficiency is a selfish design goal for DDN, but also one that benefits everybody here. Efficiency enables us to extract the most performance out of the architectures that we build, and the most performance and scalability out of the commodity infrastructure that we build it with. And as a result, we just have a lower total cost of ownership that in turn benefits all of you. So storage systems are very hard to build. We know this through experience. We've built 2 architectures now, and the system is basically what we've built is in effect a state machine architecture over 2 whole families of products that's designed for highly efficient and maximized multi-mode performance. When I say multi-mode, I'm talking about the ability to support both high bandwidth applications, also IOPS applications, but also that minimizes latency that you get associated with basically any other storage technology in the marketplace today. So things like interrupts and all sorts of different things that happen for system correction will impact almost every other storage architecture in the marketplace today, and we try really, really hard to eliminate all of that complexity and all of those challenges from our designs. And then finally, there's a second element to efficiency that we focus on, which is data center efficiency, and we'll get into that. But ultimately, where we're coming from is we're going in a direction of being able to scale basically on 3 boundaries independently. First, in terms of capacity, we have a lot of deployments starting up that are tens of petabytes behind a shared file system. Secondarily, in terms of performance, we're looking at terabytes a second implementations. We're now bidding on multiple file system projects that are talking about multi-million IOPS per second. And in both of those are capable and able to be dialed in independently with our architecture. And then finally, what we're going to be doing is extending our compute capability for pre- and post-processing as well as file system services. So what do we mean when we talk about efficient utilization of media? This is just a test that we did in Japan. Our Japanese team just did this a couple weeks ago. And they're an interesting group of characters. They basically set out to say, how fast can I run this thing with the least amount of resources possible? And effectively, what we're talking about here is 70 drives that have driven over 10.4 gigabytes a second of write performance, 9 gigabytes a second of read performance. That is, notionally about, I would say, 1/4 of what people commonly deploy the SFA systems with today. And if you have any sort of, I/O variances, I would say that, probably in architecture, a little bit more provisioned than this would be appropriate, but it really speaks to the 1.5 million lines of code that we've built into the world's fastest storage engine that are highly focused on extracting the maximum amount of performance, the maximum amount of bandwidth, but also the maximum amount of IOPS in a system. So this is actually a parallel file system test, and the throughput is excellent. It's very difficult to get numbers like this from conventional storage. And one of the ways that we can ensure performance even during anomalistic type events is through a technology that we built into the SFA called React. So when you talk about efficiency, you also need to talk about cache efficiency. And our React technology allows us to preserve the cache for very small, very random transactional events by not directing the big bandwidth applications and big bandwidth data through the cache. And as a result, what we do is during full stripe writes, we have the ability to flush those directly through or right through the cache. And then for partial stripe or small and random IOs, we mirror them over an extremely high-speed InfiniBand-based cache link. And this architecture will port forward through all of our future storage generations. But what it does is it completely automatically and without any intervention allows us to write through the cache so that we don't have to mirror data for bandwidth operations that don't need a cache, but also cache as much as possible because we're not clogging up our cache with bandwidth-oriented I/O through the intelligent I/O composition awareness that we have built into the system. So from a cache perspective, we're ready for this multi-mode, multi-user environment type I/O workload as a result of having a real-time analysis of I/O as it's going through the system. And then finally, when we talk about efficiency, we also talk about data center efficiency. The company has been in the business of very high-density storage packaging for 5 years. We were at the forefront of this with a 48-slot drive enclosure that we shipped for the, was it the 8500 or the 9500? 9500, which was released in like the 2007 timeframe, I would say. Yep. So since that time, we've been very focused on minimizing the data center sprawl that's associated with large I/O and big data. If you go by a U.S. metric, a rack of storage, or excuse me, a data center rack today costs you about $3,000 per month. So per rack that we save customers, we're saving them a little bit under $100,000 for a 3-year period, which is a real point of pride for us, and we don't even charge for it. So when you talk about efficiency, we have the ability to create extremely dense solutions from a performance perspective, as well as just from a capacity perspective. Using our 6620s and a new version of code that we're launching this week, we're able to approach over 22 gigabytes a second within a single data center rack. From a SFA 10,000 perspective, we'll be able to hit over 20 gigabytes a second of rack performance for read and write. That's using our low density enclosures. From a capacity perspective, each of them is over 1.8 petabytes stored in a single rack. So this continues to be a focus of ours. We'll continue to kind of drive forward with very data center efficient designs, and you'll hear more about that from us later. The last aspect of efficiency that we think our technology really brings to bear, and I hate that Mark didn't get a chance to talk because he completely changed my worldview on the notion of site-wide file systems when he gave a talk in Japan about 2 years ago, maybe 3 years ago now. So what you have is basically a conventional HPC buying cycle that's built on provisioning up storage for a single system and proliferating out that model as storage refreshes happen. And the interesting thing is that those clusters of storage oftentimes have varying degrees of performance requirements. And secondarily, the I/O times, or the heavy I/O times, I should say, vary based upon the law of averages. If I've got 4 systems that are checkpointing throughout the day, then there's a good chance that I'm not checkpointing each system at the same time. So the notion of site-wide file systems is now a very tenable solution as a result of having very stable, very scalable file systems such as Lustre, such as gpfs, that are used for basically a few different key things for a storage environment architect. First is the minimization of mount points. That to me was the easiest one to kind of get my head around. Okay, well, I just have one single system, so it's easy for me to manage my data, not having to access multiple mount points and things like this in my environment. The more discrete things are that you get things like a single vendor management, so that your management and your storage management resources can kind of focus on one technology and aren't jacks of all trade. Secondarily, you get increased buying power just by buying larger portions of storage and kind of focusing on a central store that you grow over time. But third is, the most interesting thing to me is that you're only building up bandwidth for the most demanding cluster. So in this case, my priority cluster here is 50 gigabytes a second. As I move to a centralized resource, if you assume the law of averages dictates that my I/O is going to be happening at a number of different times, then I have the ability to dramatically reduce the amount of resources that I have to deploy by only building for the most demanding cluster that are operated at any given time. So the efficiencies gained from the site-wide file systems that we're deploying and we're deploying with our partners is considerably substantial. We're seeing deployments like this at organizations like Oak Ridge, Lawrence Livermore, a few other Department of Energy laboratories, and in Europe we're starting to see some proliferation of this concept as well. So those are the key design tenets that we operate towards. There's a lot of SFA 10,000 customers in the room and some 6620 customers. So we are releasing a new version of the software this month, and I just wanted to take a second to kind of bring everybody up to speed on what's coming down the pipe. So this release is about 2 months behind schedule, I would say. And there's a reason for that. We added an additional 2 months of QA time into the release. Earlier, John had talked about our overarching focus is quality, quality, quality. He also talked about management team that's coming in. We're basically hiring a lot of people from extremely large IT companies that are coming in and saying, okay, you guys are doing great, let's see what we can do even better. And one of the things that they're doing is putting a penultimate focus on quality. As we go from being a $200 million storage company to being a $500 million storage company, this becomes increasingly critical. So our roadmap slows down a little bit as we bake everything a lot longer, but the amount of quality that we've injected into our product goes up substantially. So the 1.4 release will be applicable for both the 6620 and the 10,000. This is our first release to support 3 terabyte hard drives, which gets you a 50% increase in capacity. Some other features that come along with the release are an increased usable capacity for SSDs. We also get a reduction in failover time for those that we're dealing with failover in the low number of minutes. And then finally, additional usability. You're going to find usability is a common thread in what we're talking about with our roadmap direction. Usability in both in terms of how to manage LAN topology, how to manage command line changes, how to manage things like backing off our LUN verify capability when we're doing things like very heavy I/O. And then finally, new management procedures that we're implementing in the system to make it easier to manage and support. This all comes along with 1.4. These are not the most exciting features, I know, but kind of checkbox things that we had to build into the technology. Secondarily, this is our first system to support VMware. So all sorts of VMware-based services can be layered on top of the system. For people that are looking for virtualization stores, the 10,000 and the 6620 are now supported offerings. And then one of the big changes for this release is that we now support a new very high density 6 gigabit based enclosure that we call the SS7000. Supported for both, supported for exclusively the SFA 10,000. We won't support it for the 6620. But the system brings along a few interesting capabilities. First, it's less deep. We can fit it into more industry standard data center racks. Secondarily, it's a cooler system by virtue of the fact that we've eliminated a lot of the internal guts that we had historically put into the system. Some of you know this with the 6000 is our DEM cards. Those now live within the I/O modules. So we have less electronics in the enclosure, which means that it gets cooler. We have improved serviceability. We don't have the kind of clasp that people didn't always have the most fun time with when they were opening and closing the 6000 base enclosures. So the system is a high-density enclosure used for the SFA 10000. Also will be available for future generations of scalable DDN arrays. Okay, one of the other important points about the 7000 is it also supports the S2A 9900. Future shipments of the S2A 9900 will feature a 6 gigabit SAS capability. One of the nice things about moving to 6 gigabit and moving to a faster interface is that first and foremost we get a little bit of a performance bump, around 10%. Secondarily, moving to this new architecture allows us also to change the way that we manage drives. And now the dongles that we have in the system are also capable of basically the dongles are capable of converting SATA protocol into SAS. So that means that as we put SATA hard drives into a system 3 terabyte and beyond, they're actually viewed as SAS drives. And the lack of protocol translation within the system and lends itself to a more robust user experience. We don't have conventional SATA failures like you would in a full SAS to SATA implementation. And because the drives are talking SAS now, they're considerably lower latency. Okay, one of the other nice things about the new release is it also supports a high-density, low form factor 2U, 2.5 inch drive enclosure. This is how we get to the 20 gigabytes a second in a single rack through the implementation of our SS2460 disk enclosure. We can configure this up to 120 hard drives, about 7 gigabytes a second in a file system with 10K SAS drives today. This is more for customers that don't need a lot of capacity but are looking for reduction in space, power, depth, and weight as they build out high-performance storage systems. I covered the SAS SATA interposers that we're shipping with the system. Our drives are now native SAS, even though they may be SATA in design. When they're talking through the storage system, this, as I mentioned, reduces the amount of exposure to SATA anomalies, but it also it reduces the number of cascaded failures that happen in a SATA-based system. We also get a performance boost. As I mentioned, SFA 10000 can get up to 14 gigabytes a second. That's peak performance. It's not something that we'd sign up to in a sustained environment, but there's also a 10% boost in our sustained performance as well as a result of this. And then the 6620 is back up to the level that we'd like it to be, 2 gigabytes a second of read and 1.6 gigabytes a second of write performance in SATA configurations. So that's the product update that we have. I wanted to take a little bit and just talk about our roadmap highlights. Now, a roadmap for us is a little bit of a delicate situation. We're moving into a mode where we're operating as a little bit more of a disciplined organization, where we're not kind of spelling out the kitchen sink in the middle of our very large user group and conference presentations. But I wanted, because a lot of you are customers and valued partners, I wanted to at least give some direction on where we're going and what you can expect in the very near term. So we will, for our large end arrays, we will expand our base platform performance substantially in a system that we're announcing at Supercomputing 2011. I took out the numbers just to make it a little bit more tough for everybody to figure out, but expect that we're going to get at least more than a 2x bump in our overall system performance. That system will get a slight refresh in 2012, but from a gigabytes per second and an IOPS perspective, we're going to be substantially increasing the performance of systems. We've already started to pre-announce some awards that we've gotten from this system in terms of deployments that we're making. Some of the other things that are driving the roadmap, additional MTDL increases through very intelligent drive management. We'll start to announce this type of capability at Supercomputing 2011. Similarly, a lot of focus on usability, so there's going to be a lot of new tools and a lot of new capabilities coming out with our systems in the very near term. We'll feature increased configuration flexibility with a focus on extending our compute capability. As well, we'll be putting a large emphasis on data processing and extracting information from data. And some of that, if not all of it, will lend itself as well to a real-time capability for people that are worried about and concerned about very high levels of quality of service. So it's unfortunate Mark didn't get to talk about exascale because we're doing a lot of work right now on exascale. And there's basically a number of divergent paths that we're looking at and we're supporting in parallel as we move towards exascale. And in the discussion about application awareness of data and the usability of POSIX when you get to systems that are 1,000 times faster than what are available today really becomes interesting, and we're having a lot of discussions with leaders in the supercomputing community to look at the trade-offs of a POSIX file system versus what we call NoFS. So this is an extension of a concept that's in the database community and the data warehouse community right now called NoSQL. And NoFS for us is a collection of storage technologies that have been put in best practice at organizations like Google, Facebook, Amazon, and other organizations that are building up cloud storage architectures that really eschew POSIX in favor of very high levels of scalability and efficiency at scale. So we're going to continue to advance with very high performance file systems. These include Lustre, gpfs, and we'll start to see PNFS creep out into the marketplace next year. But we're also looking at the capabilities available to us from a NoFS perspective, and even leveraging NoFS capabilities as an underpinning for some parallel file systems. So here's just a quick comparison that we did based upon numbers that have at some point been recently published, but also the DARPA numbers have been around forever and ever and ever. Comparing some of the technologies that are available today, this PERCS requirement is also associated with the DARPA project, where DARPA, the HPCS, went out and decided what would be the most demanding file system challenges for the next N number of years, and they solicited a number of technologies to go off and try to meet those. And while it's commendable from a file system perspective, it showcases the kind of limitations that computer architects bring forward when you're looking at extremely scalable file systems. So just looking at the number of reads and writes per day, which is what Google set the baseline for with their Megastore product that they just announced. And it's not a product, it's an internal service that they built, which is one of the fastest storage platforms in the world. And then we compare that to WAS, which is our hyperscale object storage platform that doesn't have conventional storage file system capabilities like locking and metadata support, but does support extremely high levels of scale out for applications that have an awareness and an understanding of their data, which we're seeing as a trend going forward with a lot of our customers who are looking to build more and more intelligence into their application layer. A concept like WAS may be appropriate. So WAS, we believe, as well as some of the other work that we're doing, is getting ahead of an information explosion 2.0. This is a supernova of data creation that's really brought on by things like smart machines, social media, mobile devices, a lot of what we call machine-generated data. I think Sanzio had talked about how data is increasing at a rate faster than Moore's Law. The reality is that machine-generated data will grow as fast as Moore's Law allows it to in terms of the volume of storage consumed every year. And DDN is on the path to capitalize on this trend by today being the worldwide provider of very extreme storage systems that power high-performance applications. Tomorrow, we expect that we'll be an information analytics company that is powered by these same extreme storage systems. So we'll use and we'll continue to partner with the HPC community as our guiding light for the designs that we're bringing out going forward. But what we want to be ahead of is people dealing with an unbelievable amount of data that they've created and not an understanding of how to extract the signal from the noise. So we believe that we're very far along on the path. We've got a collection of very scalable hardware platforms that are used to power the world's fastest storage systems in the world today. On top of that, we layer a number of different storage services, whether it be block, file, or moving forward, even objects or compute. And then on top of that, we're going to be moving into adding additional value by bringing to market some analytics capabilities that will allow our customers to scale with this big data trend, this information explosion 2.0, but also extract insight from data via the scalability capabilities that DDN builds into both an information awareness as well as a very scalable infrastructure. So Larry's giving me all sorts of notes over there saying that I'm just about out of time, but that's all that I have. So John had mentioned earlier that we really want to listen to what our customers are saying, and you know, what we're giving you here is a preview. We expect to have a lot of discussions with everybody over the next couple days on what's coming with DDN, as well as what you want from us going forward. We continue to be driven and motivated by your wallets as well as your thoughts, and as John mentioned, it's our largest business by far, which is HPC. We continue to leverage and to listen to HPC as our guiding light for how we design and how we implement storage technologies today and tomorrow. So please be forthcoming with us. Tell us what you like, tell us what you don't like, and you can be sure that we will listen. So that's all I have. Any questions? Wow.